So thank you very much to Ben and Surya for organizing this workshop, and also thank you for inviting me to give this talk, I guess keynote talk. Great honor, and I've been asked to talk about what is exploration. Now, this is in a room of experts on exploration, so it's a bit intimidating, but hopefully everyone's made the effort to come out here early morning, Sunday, dark room. So I hope I can energize you, and if there's something you find interesting, or particularly if something you disagree with, just shout out, and let's get this day going with a bit of a bang. So yeah, thank you to everyone there. Thanks to, I guess, some of the work and learning about exploration did at Stanford, my advisor, Ben Van Roy, who's here, and I guess a lot of the thinking and stuff on this subject is really shaped by him, and two great co-authors on a lot of this work, Dan Rousseau, Zheng Wen. I'm now a research scientist at DeepMind, and working with so many great people. John Aslanides, who's over there, we've been working recently together a lot. So I mean, there's really too many to name, but so thanks. So I guess before we go into exploration, I'm going to say, well, what is reinforcement learning? And probably you've been through so many of these slides at ICML, you're totally sick of it. But let's do it one more time. Agent interacting with an environment. You'll receive observations, you'll take an action, and your loss function is the reward, and your goal is to maximize the reward through time. Okay, and so reinforcement learning can be viewed as, I guess, a special type of active learning, or maybe it's not even that special. So active learning, multi-arm bandits, Bayesian optimization, this is typically framed as, at each time step t, you take an action. You interact with some function, and you receive an output. You repeat this system in order to accomplish some reward. Well, reinforcement learning is really just a special type of active learning, where the action that you take can be viewed as a policy. And you interact with an environment, and I guess the output just has a special type of structure. So these are typically broken down into state, action, reward, next state. Okay? So everything we do in reinforcement learning can be viewed as just a special case of this active learning paradigm. And in active learning, people talk about exploration-exploitation trade-offs, so it's no surprise that the same kind of thing shows up in reinforcement learning. So within reinforcement learning, I wanted to highlight, I guess, there are so many aspects of reinforcement learning that people, I think it was 17 sessions worth at ICML. It's really amazing. But I guess I wanted to break down important aspects of reinforcement learning into three kind of distinct areas as I view it. So the first thing is, to do reinforcement learning well, I guess you have to be able to do supervised learning. And I guess you also have to be able to do unsupervised learning. But overall, we could just call these learning from data sets. If I have data, I have to be able to make sense of it and try to get information out of it. And I guess the key word for that, or one of the key ingredients of that, is generalization. I want to be able to take a data set, and I want to be able to spot patterns in it, I guess, which hopefully extend to new data sets or not exactly the same thing. And I guess that's a form of knowledge. And generalization is really, really important. But I guess neither supervised nor unsupervised learning deal with the problem of partial feedback. So I guess this is taking actions. And I guess when you add actions into the mix, this is a problem which is commonly known as, I guess, multi-arm bandit, or active learning, Bayesian optimization. And I guess the real trade-off here is the exploration versus exploitation trade-off. Okay? And in the workshop of exploration, I guess that's really short for exploration versus exploitation. How the actions you take affect the data that you get. You're actually interacting with the system, and often this throws up a trade-off of optimizing given what you know so far, exploitation, versus gathering information to do better in the future, exploration. Now, you might say that, okay, well, this is basically everything. But I guess reinforcement learning and the structure of reinforcement learning looks at one or more problem, which is that of long-term consequences. So the learning problem at each time step might influence actions, information, and even the underlying system at future time steps. And I struggled to find a great word for this, but maybe we could say this is a credit assignment problem. And overall, as a field, I guess machine learning, reinforcement learning in general, I think if you pick any two of these things, we're pretty good. So, generalization with exploration, people have done great work in, contextual bandits with function approximation. And if you pick exploration with long-term consequences, well, we're pretty good with, tabular reinforcement learning algorithms. We understand that really well. But I think the challenge for the field going forward and reinforcement learning in general is how can we get all three of these things into a computationally efficient algorithm. And now I'm here talking about the exploration problem. We're here for a workshop, but I don't think you should come away thinking that this is the only important thing. Generalization is obviously extremely important. Credit assignment, very important. But if we're just going to highlight what is exploration really about, I've got a bit of a impact slide coming up here. So most of AI and machine learning focuses on big data. So you're getting a huge data set trying to get knowledge from it. Exploration is about gathering smart data. Do you get the right data that you need to make your decision? Okay? We can say that every more and more gigabytes of data are being gathered every day, but if it doesn't have the right questions, then no machine learning algorithm is going to be able to learn to make good decisions from that data. You need to get the right data, and that's what the exploration problem is about. So I guess after that, I'm going to just jump into an example and a video, because hopefully that'll make these things a bit more real. And it's, it's one of the most classic reinforcement learning problems around, cart pull, but we've just changed it a little bit. So the only difference is you do cart pull, but you start at the bottom, and you have so the pole is hanging down, and you have a small cost for moving. And you only get a reward when the pole is upright, and it's in the middle, okay? So you got to really balance the pole and hold it steady in the middle. And I guess what I'll say to you now is that a lot of state-of-the-art deep RL is pretty much useless in this problem. So this is meant to be a bit of a joke here. We got deep exploration, or deep space, okay? So I guess the point here is that cart pull, most of you will have seen cart pull, and you'll have seen it as like an intro problem for reinforcement learning. So this is not meant to be like the grand challenge of AGI, right? It's meant to be pretty easy and obvious. But I guess what's worrying is that when you look at some state-of-the-art algorithms, this is DQN or DDPG, so they start off, you're trying out random things, moving the pole, but you don't really get anywhere. And after 500 episodes of interacting, all you really learn is that moving is bad. It costs money to move, so I'm going to move less. So this is the exploitation. And by the end, 1,000 episodes, you've just learned to do nothing. You'll never learn anything. You've completely failed. So like all good space dramas, there is hope, because if you use deep exploration, and I'll say what that is later, you start off and yeah, you can't do anything reasonable at the beginning. But this is an algorithm that wants to, searches out new information over multiple time steps. And after 500 episodes, you're sort of seeing a little bit of reward. And after 1,000 episodes, well, this has totally, learned to balance the pole really well. So that isn't to say that this is the most, pressing concern of the field, but I think it's worrying. And the press are in attendance here, the AGI is coming soon. Well, it's worrying that the sophisticated methods for artificial general intelligence can't work out how to swing the pole up, all right? And if we really are interested in robust systems for artificial intelligence, well, we need to make algorithms that can address this type of failing. So I've used a buzzword here, deep exploration. What is deep exploration? It's not exploration with a deep neural network, or at least that's not how we're trying to use it. So please don't blame me for that misnomer if it gets used. But I'll use another example to explain what deep exploration is. Imagine you have a mouse that interacts with a maze repeatedly through time. And this mouse, you put it in, runs around, tries to get cheese, all right? And after being in this maze, maybe 100 times, it's explored some portion of the maze, and it doesn't know what's in the other portion of the maze, right? That's the gray area with the question mark. But it knows that, I guess, there could be something bad, a mousetrap in there. You don't want to get hit by a mousetrap. Or it could be something really great, like birthday cake. And yesterday was my birthday, so if anyone wants to get me some cake later, I'm open to it. But the mouse doesn't know. But what it does know is, given the information so far, it can leave the maze almost immediately and get a bit of cheese, okay? And that's good. So that's sort of the exploitation. But if the mouse wants to learn anything, it has to make a beeline all the way through the maze to the area that's unknown, right? And the issue is that if the mouse is optimizing its current goal, it's extremely unlikely that a series of epsilon greedy, random actions or exploratory actions will take you to the question mark, right? So in order to get to learn anything new, you have to go all the way here, but you have to take all of these actions. Maybe this is 20 actions, 50 actions, something like that. And you don't learn anything on any of those individual actions, right? People normally frame exploration versus exploitation as this choice, or either I'll exploit or I'll explore. Well, here, in order to explore, you need to take an action that leads you to somewhere where you can explore in the future, right? And that's what deep exploration is about. Deep exploration is about exploration over multiple time steps, planning to learn. And I guess to break this down, by motivation, the rat can easily be motivated by reward or information. And we can look at that over a single time step. So a single time step, you can be myopic in your optimization, or you can be myopic in your exploration. But in dealing with reinforcement learning, you might need to take actions that set you up for later in the episode, right? And so that's obvious, a value function. To get to the cheese, you need to plan over multiple time steps. But I guess it's slightly less obvious that you need to also do that for exploration. And that's what we're calling deep exploration, right? And I mean, I'll add some references later on. This isn't a concept. We're not the first people to recognize this concept. It's really, there's a whole field of literature basically dedicated to this term. But I think it's an important point to highlight. So if there's anyone who has some questions about deep exploration, please shout out, or I'll take the questions at the end. And so while I'm on the series of examples, I'll just start with another example. And again, it's a very stylized example. But I guess imagine that the world is this sort of grid world. It's really simple. It's an n-by-n grid. And you're imagining that you start on this boat, and each time step you fall down, and you want to check out this treasure. Treasure could either have something good or something bad, right? And the actions are tabular, so you can either go left or right, but they're tabular. So the action 1 or 2 could be different in each state. And so you either have something really good in the chest or really bad, but there's a bit of a cost for moving right. So all the way until you make it all the way to the end, you pay a cost. So this is just really a very stylized, sanitized version of the cart pole problem that we had, right? It's like the mouse going through, it has to forsake the cheese that it knows about in order to look for other cheese. And you shouldn't think about this as like, oh, this is the problem that we want to solve. It's evocative of this kind of trade-off that might happen a lot. If you're a robot trying to do something, you may have to give up you might not always follow a policy gradient of strictly improvement in order to learn what you need to learn. But I guess the issue with why this problem is interesting is that there's more, 2 to the n minus 1 policies guarantee a negative reward, right? So basically or 0. So they're all really bad. But there's one policy that might be good, right? And that's the policy of going all the way from here, opening the chest and finding that there's there's money. Okay? So it's really like a needle in the haystack problem of policies. And if you take most of our algorithms that we have at the moment, epsilon greedy, Boltzmann exploration, policy gradients, evolution, take all of them, they're going to take 2 to the n episodes, at least, to learn, right? Because they basically have no way of learning from the signal that they have. But if you do deep exploration, you can learn this in like n episodes. And what is the deep exploration is saying, hey, I want to learn what's in that chest. Well, I just need to learn all the n things in between. Okay? And I guess the more interesting thing, sorry? I guess in this thing, this stylized version, the agent sort of has full observation of the state and the system. But in some of our recent papers, we do a version of this with neural networks where an encoding is a one-hot encoding of a pixel. But I guess these exact statements are more tailored to this, full information state. But and then I guess another interesting thing is that if you do this with generalization, so this is an important, I guess, Katya, this answers another one of your questions. Imagine if instead of observing what state you're in, you observe just features of the state. And now this is a very toy example, but we say, oh, we give d-dimensional features and the true value function lies in the span. Now this first statement is, I guess, totally true and proven. And I guess this is more of a goal and I guess an empirical observation of some algorithms that do exist. But the goal is that if you have a d-dimensional observation, well, maybe you should be able to learn in d much less than n. Okay? And this is the goal of deep exploration with generalization. And I guess I'll have a reference there to a recent paper we've put on arXiv. But that's sort of a thread of research that's been going on for a few years. So what is deep exploration? An algorithm that plans to learn. And I'll tell you that we need to have algorithms that demonstrate deep exploration. So when you talk about performing deep exploration, I'll leave that up for a bit, we need to have a coherent objective to sort of guide the field and progress our research. And I guess what I would suggest to you is that good exploration is not about solving Montezuma's revenge. If you come in here and you say, oh, I've got an algorithm, it solves Montezuma's revenge, it's great, but it's not really clear that that solves the exploration problem for us as a field. And one way to think about it is that we have the space of all possible environments. We have a family of environments that we might be interested, and you might look at a single problem. And a goal of an exploration algorithm, an ERL algorithm, could be to perform well across a family of environments. And one way of formalizing perform well is you might look at the regret of an algorithm. Regret is of an algorithm to time t of an algorithm pi in an MDP M. You might look at the shortfall in the cumulative rewards minus the rewards you actually get. And I guess you could say the Bayesian regret for a distribution phi is the expectation of the regret where the environment is drawn from that distribution. So this could be a reasonable goal for algorithms is to design algorithms that have low Bayesian regret for your specific problem, where phi determines the sort of problem you're interested in. Now you don't need to be like totally Bayesian about this. We could do a worst case bound as well. We might say what's more commonly called as the worst case regret. And you say, oh, the worst case M across any family of interest. But I don't think that that distinction is hugely impactful for most problems of interest. And when you want to maximize your expected return, this is if and only if you're minimizing your base regret. So I think this is a good thing to aim for, and it sort of matches our goals in reinforcement learning. Of course, we also need to consider robustness, and I think that's a really important, if your distribution of phi doesn't exactly match the environments that you're evaluated against, is this a rigged problem? So I guess exploration is kind of an interesting problem, though, in that we already know how to solve that objective. You just solve for the Bayes optimal solution, right? So this is kind of an anticlimax. Why are we bothering with this whole workshop, with these talks, with these weird algorithms? Well, I think the issue is that Bayes optimal computation is computationally intractable. You might need to consider scenarios that grow exponentially in the problem horizon, and direct approximations can fail spectacularly. So I just got a citation there, but there are many examples, even on simple problems. And I guess the literature and work on efficient exploration is all about trying to get good Bayes regret, good statistical efficiency, but also maintain computational efficiency. We need to remember that. And I guess so why are we bothering with analysis? The press are here. I'm sure it's not to discuss whether we've tightened a new regret bound from S to square root S. Okay. We want to have exciting things, and we want to do real problems. And why would we spend our time bothering with analysis and theorems? Well, I guess the first thing is that this stuff is meant to provide sanity checks for our work. If we can come up with, if we can't prove that something works on this sort of simple setting, well then maybe this is indicative that our algorithms have problems on a more complicated setting. Now the reverse isn't necessarily true. Just if you have an algorithm that's good on toy problems doesn't mean it will be good for solving AGI. But I think if we can't solve simple problems with our general intelligence, then I think this should be cause for concern. I guess performing this type of analysis and work helps us to understand the computational and statistical trade-offs. We get a much deeper sort of, assurances and rigorous safety guarantees than just, simulating on a few simple domains. And I think that the most important is actually, if we do this type of analysis, we can get some insight into how the algorithm actually works, what the key issues are at play in an exploration problem, and if and how the algorithm accomplishes these goals, and this can lead us to make better algorithms. So I'd encourage people to keep this front and center, or at least a concern in the design of good exploration algorithms. So I've mentioned deep exploration, and I say there really is a theory of deep exploration which has which guarantees that if you perform deep exploration, you'll get a regret over L episodes that's sort of polynomial in the amount of parameters of the problem, as opposed to exponential. And I think, highlight starts with Kearns and Singh, 2002, but, sessions and sessions, so much work, great work done in this area. But I think that the focus has mostly been on tabular models, right? And that's why when you look at most of the talks in reinforcement learning, they're kind of, at ICML, very few of them build on this thread of work. Very few of them demonstrate deep exploration. And I think it's because if you don't do generalization, you don't address problems of practical scale. It is a good sanity check. It's good inspiration. It's a good basis. But it's not going to take us where we need to go. And I guess I hope that this talk inspires people to build towards a principled and scalable approach for exploration with generalization. Oh, people taking photos. So I'm on to my final slide here. I'm not really going into much detail about specific algorithms. I hope that during the rest of the day we're going to hear so much about great approaches. But I'm going to put out 3 points that I think make a wish list for what we might want for exploration. So the first thing is, I think you have to pass simple sanity checks. I guess particularly in terms of deep exploration. If we're making AGI, if we want robust artificial intelligence systems, we have to be able to solve these kind of simple problems. Otherwise, we're going to run into real problems on real systems. We need to have exploration with generalization. Now, this generalization, though, importantly, we need to specifically seek out information that improves our decisions. Right? It's not good enough to just seek information about everything in the world, because it'll take us too long. There are too many states, there are too many things to learn. We need to seek out information that is directed towards our decisions at hand. And the final thing is that it needs to be computationally efficient. We need to be able to scale this approach to large problems and combine it with flexible, deep learning, just large-scale problems, and so that we can impact real world. And so with that, looking forward to see what happens during the rest of the day, and hopefully all 3 wishes will be granted. So thank you.
So this isn't exactly a question, it's more of a comment, but 1 and 2 we've been able to do, and there's an archive draft doing a version of 3. I'm not satisfied with it yet, but it's a progress.
Yeah, so I think that if I was going to highlight a piece of work, I think, we were highlighting a piece of work that I guess I've done with Ben was via randomized value functions. I think another piece of work is by yourself with the contextual MDP framework, and I think that you'd roughly agree with this kind of checkmark system. 1 and 2, yes, and 3, kind of not really. And I think that could have easily had a reference to you there. But if I want to highlight another piece of work, please check this out. Please check out John's work, and let's make it better.
Thank you for your talk. I remember you mentioned somewhere that aside from computational issues, minimizing the base risks of exploration. Is that the right way to think about it? I was a bit confused because you probably want different policy in the beginning of the learning and at the end of the learning, because you want to gain more information in the beginning and don't want to gain so much information in the end. So why is that statement possible to solve exploration exploitation trade-off?
Well, I guess the first thing is you have to say, if we're going to solve the exploration problem, we need to have an objective and define what we mean by solving it. And one objective, which I guess I threw out here, but doesn't have to be the only one, is that you solve exploration by minimizing your Bayesian regret for a problem. And I guess then, by definition, you minimize the Bayesian regret by solving this Bayes optimal computation. But I think your question was, okay, well, how can you possibly do that? Well, the Bayes optimal policy, I think, would end up doing these kind of trade-offs of, at the beginning you want to explore more, and at the end you want to exploit more. But it just would happen automatically from your objective.
But that was the same pi for every t, right?
For the same what?
For every time step t was the same policy pi.
I don't think it would necessarily, sorry, the pi I meant in that one was a learning algorithm pi. And then I think that the Bayes optimal solution to it would be adaptive.
Okay, thank you.
Thanks a lot. Cool. Thanks a lot, everyone.
All right, let's thank Ben one more time.